Okay, so I had finished by saying that if we go back one more, sorry, yeah. All right, so that negative temperature coefficient behavior doesn't come from the reverse of R plus O2 gives RO2. It comes from the competition between, we say, RO2 going to olefin plus HO2, or QOH going to cyclic ether and other beta fission products, and or going to adding to O2 again in the second addition, going to chain branching. Okay, so it's the competition between propagation of, in this case, the hydroperoxy alkyl radical for neopentane, or in other alkanes, RO2 and QOH, not going to O2, but going through propagation channels. Okay, so that's what causes an NTC behavior. All right, so intermediate temperature chemistry then. What we're focusing on here is the RO2 elimination, giving you olefin plus HO2, right? And so where do we get the Ray constants for this reaction? Okay, they're actually still not that well known, right? The more quantum chemistry calculations that have been performed, the better well known. The first calculations of it were actually in the mid-90s by Quelch et al. First proposed that ethyl plus O2 giving you ethylene plus HO2 had a cyclic transition state. Okay, and then Miyoshi used variational transition state theory and RRK and master equation analysis to look at ethyl, isopropyl, N, S, and T butyl plus O2 and calculate Ray constants for the concerted elimination from those species. Okay, then Villano calculated 23 different straight and branch chain alkyl peroxy radicals, and Franklin and Goldsmith, where is it? Okay, here, calculated the propyl plus O2 system. Okay, so we need further studies on these reactions due to their high importance and the continued uncertainty in the Ray constant of those reactions. Okay, I'm not giving you bounds and so on, but the more calculations that we have and the more validation that we have, the better known those Ray constants will be. Right. So again, so I had highlighted last time RO2 given olefin plus HO2. Now I'd like to highlight fuel plus HO2 giving alkyl radical plus H2O2. So once we form the HO2 radical, that radical can go back at intermediate temperatures, abstract from the fuel mostly because that's the highest concentration stable species that is in the system, right? And that gives you fuel radicals and H2O2. So you get more fuel radicals, then we get more RO2, then we get more olefin plus HO2, and we have this cycle of HO2 formation throughout until all the fuel's gone, right? And then once we produce H2O2, though, at 850 to 1000 Kelvin, this H2O2, I presume you all know, but I just draw it on the board here. H2O2 is H-O-O-H, okay? And then the bond that breaks is the OO bond, right? And once you reach 800 or 850 Kelvin, it depends on the pressure, that OO bond is easily broken. So once you form H2O2 at intermediate temperatures, it'll break almost immediately into two hydroxy radicals. And that gives you branching because you have a molecule and you're getting two radicals from that. So ultimately, and this is something I say in my papers a lot, right? If you have any molecule, typically the fuel, but any molecule undergoing H atom abstraction from the fuel by HO2, you get H2O2. So one HO2 ultimately produces two hydroxy radicals, and that's branching at intermediate temperatures, right? So one radical is giving you two radicals, right? Now, there is competition. So there's another reaction that can occur. HO2 can react with itself. HO2 plus HO2 giving you H2O2 plus O2, okay? So it can give you H2O2 plus O2. And that actually is not branching, it'll be propagation because you've got two HO2s giving you one H2O2, and then you get two OHs from that, right? So in that case, you have two HO2s giving you two OHs. So that's propagation, not branching, right? So when it self-reacts, it's a propagation, ultimately. Okay. So anyway, what about then, how well do we know fuel plus HO2 reactions, right? And the answer is not as well as we would like, right? So there are a few direct measurements of H atom abstraction by HO2 because you just can't get a precursor for HO2, okay? So Amer Farouk, who did work, he did his PhD working with Ron Hansen now, he's a professor at Coast for many years now. He's done a lot of studies, as I said before, looking at fuel plus OH, and he's measured rate constants for that. But you have a nice precursor for the OH, it's some peroxide, and then you get the OH, so then you can study whatever it is plus OH, okay? We just can't get a precursor for HO2, okay? Jemmy Alade et al. Studied formaldehyde plus HO2 using flash photolysis, but this was an indirect measurement of the rate constant of that reaction. You can have a look at that. And then Ray Walker actually did a lot of studies back in the 70s and 80s, okay? And his work is very, very good, right? And it's, to this day, it's still very reliable, okay? Of different molecules plus HO2. And then he published a review in 2002 that was nearly at the very end of his career, where he published rates of reaction of HO2 with lots of alkanes, aromatics, and other related compounds. Okay, and that's a good review that if you're interested, you should look at. Okay, but there has, we are as a community making progress in HO2. So we have quantitative measurements now of HO2 radicals. And that's a step in the right direction, because at least if models can quantitatively match the radical concentrations that are measured, then we can say, well, that's one way of capturing the chemistry at least. And it gives us some confidence that the model is right, okay, if it can quantitatively match the concentrations, okay? But we can't measure the rates with other species. So, and all of these studies, so there was a kind of a race between different groups to do this because of its importance, right? So there was a study by Bloquet working with Frédéric Bertrand-Leclerc and Christophe Fitchen in France that used fluorescence assay by gas expansion to study this. And they were really the first to show quantitative measurements of HO2 radicals, okay? But almost simultaneously within a year, okay, Professor Ju here at Princeton, working with others, published a work on using Joule modulation Faraday spectroscopy to measure HO2 concentration. And then a group working with Professor Philippe Dagot and others, this is Guillaume Dema, Philippe Dagot, and others, published a cavity ring-down spectroscopy method to quantitatively measure HO2 radical concentration. All right, so that represents good progress. Here's a work that was done in my group about almost a decade ago now, looking at methanol oxidation at low temperature and high pressure, right? And you can see actually what's all important is actually this reaction, H atom abstraction from the fuel by HO2 forming hydroxymethylene radical and HO2. Huge sensitivity to that. It's the most sensitive reaction. It's even more sensitive than H2O2 decomposition, giving you two OH radicals, right? And so it's particularly important in this case, okay? But we went to the literature, and at the time, the ON study wasn't available, but Stephen Klippenstein at Argonne calculated the rate constant for this reaction, which is this magenta line here, okay? And then Eleku and Truller did a quantum chemistry calculation similar to that of Dr. Klippenstein, and his rate constant has a similar activation energy, but is nearly an order of magnitude faster, right? And there's an Alterawa-Ne calculation also, which is faster again. Okay, so these are quite diverse, and normally you don't see such big discrepancies in rate constants. They might be different by maybe a factor of 2 to 4 in rate constant. I was talking yesterday about, what was it? Methanol plus OH, giving methoxy plus H2O, right? There was about a factor of 4 or something, 5 uncertainty there, right? But not this degree of uncertainty, right? So this is then predictions of ignition delay times that were measured by Alton Burke in my group for methanol mixtures. I presume these are lean, stoichiometric, and rich conditions. And you can see that if we use the Alterawa-Ne et al. Rate constant, we're a bit fast in predicting the ignition delay times. If we use the optimized rate constant, so sorry, I should have said that in the previous. So this et al. Study was, again, an optimization study of a methanol mechanism by Thomas Tariani's group in Budapest, okay? And this was the optimized rate constant that they had from their study, which is actually similar to the Aleku and Truller, but a bit faster than their calculated value. Sorry. Then if we use the Aleku and Truller rate constant, we're too slow in predicting the ignition delay times. And if we use the Klippenstein et al. Rate constant, we're way too slow. It doesn't work, right? So, but I asked, Stephen Klippenstein is probably the best quantum chemistry person in combustion, right? Or among them anyway, if not the best, right? And he said, no, Henry, there's nothing wrong with my calculation, right? But we did this study before he did the study on HO2 plus HO2, giving you H2O2 plus O2, and then that little bleed of 10%, giving you 2 OHs plus O2, right? And I'm putting my hand up now and saying, I've never gone back, right, and looked now at our most recent mechanism with that rate constant in it, and then redone this calculation with the rate constants to see how that comes out now, right? And I would say probably the Aleku et al. Rate constants might best model these ignition delay times. I don't know. I haven't looked at it in a long time, okay? But you see that, okay, so let me go on to the next slide. I prepared this slide when I gave my plenary lecture five or 6 years ago at the symposium. And I said, okay, the Klippenstein reported high sensitivity to this, the Alterna and Lacu. But what I said at the time was, is there possibly a chemically activated reaction involving HO2 radicals that's occurring, right? I'm not trying to give myself a slap on the back. I don't mean it like that, right? But that was the discussion that we had at the time about this, right? And there is actually. It's HO2 with itself, giving H2O2 with that bleed to 2 OHs. So I think if we go back, I haven't done it, as I said, I wish I did. And I should before I give the next set of lectures. But I would imagine that this Aleku et al. Rate constant, the predictions would certainly be faster, and they may align now with the experimental measurements if we include Stephen's calculation for the HO2 plus HO2 channel, right? So, but don't worry about that. This analysis and this study was telling us that there were things that we didn't know yet, right? And then the fact that Stephen went back and did that calculation on HO2 plus HO2 has enlightened us more. And maybe now, and I don't know, like another, like Don Truller is certainly another like very an excellent guy in quantum chemistry calculations also, right? He would be on a par with Stephen, okay? So the fact that his ray constants calculations and those of Stephen's didn't agree, I'd love to sit the two of them down and we spend a day or two going through what was wrong with the calculations. That they'd probably be able to work out what went wrong or where the problem lay or whatever it is, right? But, you know, unless, you know, bring a gun or do something, you can't make people do that, right? So you try and elicit what you can, okay? So that's that, okay? But actually then there hasn't been a lot, or certainly up to recently, there hadn't been a lot of calculations of fuel plus HO2 reactions in the literature. They're not as well known, essentially because there's been very few experimental studies because you don't have a precursor for HO2, okay? You can't make HO2 is the problem, okay? So Carstens and Dean looked at methane, ethane, propane, and butane plus HO2. And then because of their importance, one time when I was, I actually went and I worked with Wim Klopper's group in Karlsruhe Institute of Technology in Germany. That was maybe 10 or 15 years ago. And when was it? 2008. It was nearly 20 years ago. 15, more than 17 years ago, right? And we calculated ray constants for methane, ethane, propane, N-butane, and isobutane plus HO2. And our calculations agreed well with the determinations of Walker et al. So the measurements by Ray Walker or ray constants agreed better than the calculations by Carstensen and Dean. I'll show you some calculations or some comparisons in a second. Okay, so here we have it. Okay, so here we have propane, butane. This is giving you N-propyl radical. This is giving you the secondary butyl, right? This is giving you this is secondary H atom abstraction from propane. And then this is primary H atom abstraction from isobutane. Okay, so the point here is the Baldwin-Walker measurement, right? And then the solid line calculation here is from the work that I did with Wim Klopper's group in Karlsruhe, right? The red line calculation is from Carstensen and Dean, okay? And actually, for primary fuel plus HO2, they're faster than we are, right? And actually, most recently, in our mechanisms in Galway, we've increased the ray constant of primary H atom abstraction from a fuel by HO2. We've increased the rule that we use, the ray constant that we use for primary hydrogen abstraction is closer to that of Carstensen and Dean. But you can see that for secondary, okay, there is no calculation, but these are the recommendations of Scott and Walker, okay, here. And we're faster, but actually Carstensen and Dean are significantly faster. And in all of the cases here, using quantum chemistry, Carstensen and Dean are significantly faster than we are, okay? And again, this is primary, and you can see that they're actually closer than we were for the primary. And actually, we've gone closer to, for the primary, we've gone closer to them. But for secondary and tertiary, we've stuck with the ray constants that we have, okay, over the years, just to say that, okay? But again, look, that isn't the point of this. The point of this is, look, at intermediate temperatures, HO2 radical chemistry is very important. And it's important to have good ray constants for abstraction by HO2 if you want to predict the reactivity of your fuels correctly, okay? And this is the kind of thing that we try to do to make that happen. So if you're going to look for good ray constants, look in the literature to see have people done calculations on fuel plus HO2 chemistry and calculated ray constants for those. Okay. I've been focusing on HO2 because HO2 comes directly from RO2, that reaction RO2 gives olefin plus HO2. But actually, at intermediate temperatures, we'll say 825 Kelvin here, and maybe 1,000 also. You can see 825 Kelvin, right? Fuel plus OH is important, but 825 and 1,000, look at fuel plus CH3O2, right? Giving the 4 isooctyl radicals plus CH3O2H. They're really important and sensitive reactions in a mechanism. So any molecule, right? Sorry, why is it important here for isooctane? Isooctane can undergo beta scission starting at about 825 Kelvin. Now, it's not very much because most of the alkyl radical will add to O2, but a little bit will undergo beta scission. And the higher in temperature you go from there, the more and more alkyl radical beta scission you're going to get. And the radicals from isooctane will produce quite a lot of methyl radicals because it's a branched alkane, right? Dimethyl ether will give you a lot of methyl radicals because of the structure. I'll show you the chemistry later today or tomorrow. Okay, so any fuel that can give you methyl radicals, those methyl radicals then, if you're at intermediate temperature, can add to O2 to give you methyl peroxy radicals. And then the methyl peroxy radicals can abstract from the fuel to give fuel radicals and CH3O2H. And then CH3O2H, I don't know where it is it even shown there, gives you methoxy plus OH, right? And that will give you branching, right? So it's important, it's showing up, this reaction class shows up as important for isooctane. But what I want to hammer home is that any fuel that can produce methyl radicals will equally be as sensitive to fuel plus CH3O2, okay? Reactions. And actually they're studied even less than fuel plus HO2, right, by the community, okay? So the pertinent reactions are methyl plus O2 giving methyl peroxy, and then they abstract from the fuel to give the radical plus CH3O2H, and then that gives you methyl peroxy, methoxy plus OH, okay? Again, Carstensen and Dean, I think in the same study as I showed for HO2, looked at methane and ethane, and plus HO2, methyl peroxy, and ethyl peroxy, okay? And then a further study, a couple of years later, extended that to look at other species, methane, ethane, propane, butane, plus CH3O2, okay? So, but there's been very few other studies of those, right? And actually, they're necessary for fuels that produce CH3O2 molecules. Okay. So so if we go to the low temperature end then, okay, or in general, sorry, I should say, we want to have a way to estimate rate constants for all of the reactions that occur, right? So we have unimolecular fuel decomposition. We have H atom abstraction from the fuel. We have alkyl radical formation, then it's beta scission to give olefin plus RO2. And the relative rates of this, so you have alkyl radical adding to O2 to give RO2, or alkyl radical undergoing beta scission, that's going to decide at intermediate temperatures differences in reactivity, right? So the branching ratio of those is going to be important. So the rate constants that you use are very important, right? And so all of these reactions that occur along the way, we need a way to estimate or calculate the rate constants, right? And now these are for big molecules. And we don't have, like, it's not like methane plus O2, like I was talking about yesterday, or those reactions that, they're not as simple as those, right? And so there have been much fewer basic studies of those. Okay, so what this slide is courtesy of Bill Pitts, and it extends from work that we did on the primary reference fuels, N-heptane and isooctane, where we broke the mechanism down into reaction classes. So we have, at high temperature, we have 9 reaction classes. We have unimolecular fuel decomposition, H atom abstraction from the fuel, the alkyl radical decomposition, alkyl radical reaction with O2 to give olefin plus HO2, alkyl radical isomerization. Okay, so all these different reaction classes. And then we have rules that we apply. And then at low temperature, we have these other, I don't know what it is, 16 reaction classes to extend it to lower temperatures. And we had 25 reaction classes altogether when we published the N-heptane and isooctane mechanisms. We now actually have about 30 or 31 reaction classes or something like that. Okay, so, but we can study then, and people have done it, so this is the study I was talking about earlier, Vellano, I don't know how to pronounce that name, Carstensen and Dean. Okay, this was published, I don't know, in about 2009 or something. I have the reference a little bit later. Okay, but here they studied high pressure rate rules for alkyl radical plus O2 reactions, the dissociation, concerted elimination, and isomerization channels of alkyl peroxy radicals. So they studied in detail what happens R plus O2. What's the rate constant for R2 formation? What's the rate constant to form olefin plus HO2, hydroperoxy alkyl radicals? Okay, and what they looked at. So if we look at, and just to show the chemistry, this is a 5-member ring isomerization in sec pentyl radical. Okay, so we form 2 pentyl radical. It adds to O2. We get the alkyl peroxy radical. And that can go through this 5-member transition state ring to give this hydroperoxy alkyl radical. All right? And I have a rate constant written here. It's 2 times 10 to the 11 with an activation energy of 26.45 kilocalories per mole. All right? So if we have then the same molecule, so in this case, we had 1, 2, 3, 4, 5. The hydrogen atom that's involved in the transition state stems from this CH bond here, okay? That's in this transition state, giving this radical. But the hydrogen atom here can also get involved in a transition state ring, but that's actually a 6-member transition state ring to give a hydroperoxy alkyl radical, okay? But the radical site is here and not here. Okay, sorry, it's here and not there. Okay, in the 6-member ring, and the rate constant here is calculated to be almost an order of magnitude lower than here. So the frequency factor here is 2 times 10 to the 11 for the 5-membered ring. It's 2.5 times 10 to the 10 for the 6-membered ring, right? The activation energy for the 5-membered ring is 26.45. It's 6 kilocalories per mole lower for the 6-membered ring transition state ring. Okay, so the activation energy is lower, but the frequency factor is lower for the 6-membered ring. Okay, but all right, so why is that? Because, and a good rule of thumb is, so here you have 1, 2 rotors tied up in the transition state ring, right? So when the hydrogen atom is in this transition state, this rotor and this rotor are tied up, right? And because of that, the frequency is 2 times 10 to the 11, right? Okay, or when you consider that, when you take that into account, the frequency factor is 2 times 10 to the 11, okay? Or is estimated to be that, okay? However, in this case, for the 6-member transition state ring, in the transition state, you tie up 1, 2, 3 rotors. Not 2, but 3. So there's 1 extra rotor tied up in the transition state for the 6-membered ring compared to the 5-membered ring. And every time you tie up a rotor in the transition state, you lose almost an order of magnitude in frequency for the reaction, right? So that's why we decrease the frequency factor from 2 times 10 to the 11 down to 2.5 times 10 to the 10, right? Now, in the 5-membered ring transition state then, you can see that this looks a bit strained. And I think you've all hopefully been taught or taken chemistry class where they say, okay, benzene ring, a 6-membered ring, has no ring strain energy. And so it's the activation energy, it's more stable, okay, and it's easier to form, right? So the 6-membered ring is easier to form than the 5-membered ring, and that activation energy is 6 kilocalories per mole lower than the 5-membered ring, right? Because it's just no strain in the structure, okay? So, and here's the reference is 2011. So in the paper from Villano and Dean, what they did was they did a series of 5-membered transition state rings, 6-membered transition state rings, and involving primary, secondary, and tertiary hydrogen atoms in the transition state. So if I go back one, in both of these cases, in both of these cases, they're involving secondary hydrogen atoms. In this case, it's this secondary one. In this case, it's this one here, okay? But in both cases, they're secondary hydrogen atoms, right? But they did multiple primary, multiple secondary, and multiple tertiary. But what do you see in these calculations for different molecules? Like, so they did butane, pentane, multiple ones, right? They didn't do the same one multiple times, right? They did multiple different ones, okay? And where R varied in the transition, in the molecule. But you can see that it should be largely irrelevant, right? What you're really worried about is this 5-membered ring structure, okay? And what they found was, yeah, the primary were all clustered along. You could get an average here, and plus or minus, you'd be within certainly 50% or less for array constant. The same for secondary and the same for tertiary. So you could take the average of these and say that's the array constant for 5-membered ring isomerization involving a primary or a secondary or a tertiary, okay? And the same then for 6-membered ring. You have the primary, secondary isn't as convincing. There's a bit more scatter, but it's about the only one that, and then the tertiary, they only did one, okay? But what they did then was they have tables of ray constants for a primary, for 5-membered, 6-membered, and 7-membered rings. So these were the ray constants that we plotted in Livermore in the isooctane mechanism, right, in 2002. These are the ray constants plotted in 2011. But just look at the activation energies for primary, secondary, and tertiary. You can see, actually, okay, so for the 5 primary, theirs is 3 kilocalories per mole higher. But they're of the same magnitude, the same size, about. And certainly the variation in activation energy is about the same in each case. Okay, ballpark. I'm only hand waving, right? My ray constants were derived based on the knowledge that we knew at the time, no quantum chemistry calculations, but also on trying to fit the data, the model, to the data that was available. Okay, and again, the data helped me arrive at activation energy barriers that were reasonably accurate when I had no quantum chemistry calculations available. I was doing it by hand and fitting and trying to be as reasonable as I could, right? That's really all I want to say here. And you see, though, the 6-membered ring, again, the activation energy barriers are lower than the 5 because of the ring strain. And then if you go to the 7, they're about the same. They're slightly lower than the 6, but not much difference. So the 6 and the 7 have about the same, okay? But will the 7-membered rings be competitive with the 6-membered rings if the activation energy barriers are about the same? Why not?
The frequency factor.
Precisely. You're exactly spot on, right? So remember I said here that so for 5 to 6, the frequency factor decreases by about an order of magnitude. So if we calculate here, and well, they're not quite the same. They are slightly lower, right? But the frequency factor is going to dominate. And because that's an order of magnitude, this 1 kilocalorie per mole might make a difference at lower temperature, but as you go higher around 800, 800, 900 Kelvin, it's not going to make much difference. And the frequency factor is going to kill you. So the 6-membered rings will dominate. Okay, so then if we consider the fate, we then apply those Ray constants successfully in this paper that John Bugler published in 2015, 2016, that I keep referring to, right? And we successfully then modeled N-pentane, isopentane, and neopentane, right? And those rules we shared those with Professor Pitch's group, right? Prior to publication, and Liming Kai, working as a PhD, he's now a professor in China. Then he took those rules and he applied them to larger alkanes, right? So what he did was actually he used as a training set C7. I don't know whether it started as a C7 or C8, up to C11, right? And he optimized rate rules based on C7 or C8 to C11 N-alkanes. And then he said, okay, let's now make a mechanism for N-dodecane, C12. And does the model match the data or not? And it did. Okay? So that's what that paper says, right? And so then, but another thing I want to say is the fate of the ring structure is important, right? And what happens 5-membered rings? What happens 6-membered rings? What happens 7-membered rings, right? So to bear this in mind. So here's the 5-membered ring. You have this transition state, and actually it doesn't give you a hydroperoxy alkyl radical. It gives you directly almost olefin plus HO2, right? Typically, okay? So the RO2 goes through a concerted elimination reaction, giving you directly olefin plus HO2, okay? In older models, maybe I go back here, okay? In older models, we didn't have this channel, RO2 giving olefin to HO2. We had it RO2 giving hydroperoxy alkyl radical, and then it giving you olefin plus HO2. It's not correct to write it that way, right? What actually happens is it gives you direct elimination to olefin plus HO2, okay? And that's the way we write it now, okay? So it's like this. So basically, this 5-member transition state structure gives you olefin plus HO2. That's really what I'm trying to say, okay? 6-membered rings go through the 6-member transition state ring and then give you this hydroperoxy alkyl radical, which then adds to O2 and gives you low temperature chain branching, okay? That's all I want to say here. So 6-membered rings go to chain branching, right? Because the propagation reactions from this hydroperoxy alkyl radical aren't very fast, and so the addition to O2 and branching is faster. And then 7-membered rings, you have the 7-member transition state ring. Again, you get the hydroperoxy alkyl radical. But these hydroperoxy alkyl radical have relatively low activation energy barriers to form these cyclic ethers plus OH. So typically, 7-membered ring hydroperoxy alkyl radicals, right, go on to give you propagation, right? Now that distinction that I've just said is very important, right? So if you have 5-membered rings, what happens? Get olefin plus HO2. If you have 6-membered ring, what happens? It gives you a 6-membered ring hydroperoxy alkyl radical, but there's no low activation energy output from that, or outlet to propagation for that, okay? For a 7-membered transition state ring, you get a hydroperoxy alkyl radical, but there is a low activation energy outlet for that, which is this cyclic ether plus OH. This is an example, right? This R could be anything, right? Depending on the molecule that you have, right? So say it was butane that you had here, right? This would then be some sort of a butane cyclic ether. It would be just methylfuran. Sorry, it would be just furan, not methylfuran, I should say. Okay, so remember that. Okay, and I just want to use this again. I'm not sure this is in the notes, or if it is, it's in later. I included it here, and I put this in, right, just to show off and say, look, this isn't simple, right? It's complicated, and I'm trying to make it as simple as I can, okay? Right, that's really the point of that slide, right? But if we look at the fuel, if we look at N-pentane, we can get 1-pentyl, 2-pentyl, or 3-pentyl radicals, right? Let's try and simplify it, right? And we get about 50%. So we're looking here at the flux at 800, 840, and 925 Kelvin, okay? And I should have plotted that. But this will be along the NTC curve for N-pentane, right? And what we're seeing is that 50% of the fuel molecules that are oxidized give us 2-pentyl, about 30% give us 1-pentyl, and about 20% gives us 3-pentyl, right? Or leads to that. But if we get 2-pentyl radicals, right? What's that? About 72% of those go on to give you RO2. Okay? And about 12% decompose to give propene plus ethyl, right? Even at 800 Kelvin, right? So there is some beta scission going on, but a lot of them give you the RO2. Okay, as we go higher in temperature, the fraction giving beta scission increases, and the fraction going to RO2 decreases, which is what you'd expect, right? So if we have then this 5-membered ring, this RO2, what happens that? So at 800 Kelvin, as I said, we have about 73% of the fuel, 73% of all the 2-pentyl radicals. Okay. Am I right in that? No, I'm not. This is 36% of the fuel. 36.6% of the fuel gives you 2-pentyl peroxy radical. That's correct. Okay? And then the RO2 goes on through a 5-member transition state ring to mostly give you 1 and 2 pentene plus HO2. Some of it, a small amount of it, gives you the cyclic ether plus OH. Okay? So that's for the 2-pentyl radical. Okay. If this proceeds through a 6-member transition state ring, right, we get this transition state, we get this species. And then that mostly goes on to give you a hydroperoxy alkyl radical, okay? But some of it, okay, so 2/3 gives this hydroperoxy alkyl radical, but a third gives you a cyclic ether plus OH, okay? So again, most of this 6-membered ring, 2/3 of it, is giving you the O2QOH. And this is going to go on to give you chain branching, okay? And then if we go through the 7-membered ring, most of the 7-membered ring proceeds to give you the cyclic ether plus OH. Well, I would say most of it, it's actually maybe 50-50 rather than 2/3, okay? So this is just showing you the fate of the different species, okay, in this analysis for N-pentane, okay? Okay, so we can expand then our knowledge of the chemistry, of low temperature chemistry, to other classes like alcohols. So, but generally, alcohols are less reactive than their corresponding alkane, right? So N-pentanol has a research octane number of 80, and it's slower to ignite compared to pentane, which is a research octane number 61.7, right? So the hydrogen atom, alpha to the carbon OH functional groups, are the weakest, okay? And I'll show you this, I think tomorrow, right? I actually have things to show this. So De Silva and Bozelli in 2009 showed that the concerted elimination reaction actually has an activation energy barrier that's very low. It's 11.4 kilocalories per mole, right? Other concerted elimination reactions, you're talking about 28 kilocalories per mole. This is 11.4, it's really low, right? So what happens is, and this is just, I'm just showing it here for ethanol, but this happens for all alcohols. So here, think of this methyl as an OR, right? Any functional, right? But in this case, it's a ethanol, so OR is methyl, okay? This radical adds to O2, and you get this radical, the RO2 radical. And then that goes through this chemically, or this transition state, but you get concerted elimination to give acetaldehyde plus HO2. Okay? So you're getting that concerted elimination just like you would from the 5-membered ring in an alkane. But in this case, it gives you gives you the aldehyde plus HO2. Okay? And in the case of ethanol, it's acetaldehyde. Okay. And that, so, okay, sorry, I didn't complete this. So if this is our RO2, that gives you, we say this aldehyde plus HO2. It's not going to branching. Okay? We don't have a QOH, which then adds to O2 to give us branching. Right? This is an aldehyde plus HO2, a propagation. And hence, alcohols are slower than alkanes because this kind of a concerted elimination or elimination to give you the aldehyde plus HO2 happens in alcohols, which doesn't happen as easily in alkanes. Okay, so there's software for automatic mechanism development. Mamox code was developed by Eliseo Ranzi and Tiziano Faravelli back in the 90s. There's computer-aided automatic generation of large aliphatic molecules by Chevalier in 1990. Reaction developed by Morley and Blue Rock. You have enhanced by Gladys Mauriac, which generated mechanisms for N-heptane and N-decane. You have X-gas by Bertrand Leclerc, which uses different things. You have Genesis by what's his name? Kevin Van Gien. Thank you. Okay. You have, and of course, you have reaction mechanism generator. This is Northeastern University. I think I was told this. I was looking for the slide to correct this, and I didn't find it, so there it is. I'll correct it later. Okay. And so the mechanisms include elementary reaction steps in this reaction mechanism generator, and it's quite sophisticated now. Okay. So and that they include species identifiers. Why am I doing that? Okay, so I went on about this, that the negative temperature coefficient regime stems from competition in the low temperature reactivity, but you still get RO2. So when does RO2 stop, right? So RO2 stops, going on to this. So we have, this is an equilibrium, right? We have R plus O2 giving us RO2. And again, this slide is courtesy of Tiziano Faravelli. So the rate constant for addition has no activation energy. It's 10 to the 9, okay? And this is in liters per mole. It's 10 to the 12 centimeters cubed, okay? But the rate constant for dissociation is 10 to the 13 times the exponent of minus 28 calories all over RT, okay? So in the reverse direction, there is an activation energy for the decomposition. Okay. So there's competitive pathways. So R can add to O2 to give RO2, or O2 can react back to give RO2. Okay? And at high temperatures, alkyl radicals are favored over peroxy radicals. So alkyl radicals, again, because of what I showed you here, if you have R giving you an olefin plus either methyl or H, that's unimolecular because the rate constant is equal to, the rate of reaction is equal to the rate constant times the concentration of R, right? If it's reacting with O2, the rate of that reaction is equal to the rate constant times the concentration of R times the concentration of O2. And you can see that the concentration of O2 can limit you by 5 orders of magnitude, right? So there is a ceiling temperature, and this is the transition temperature from one mechanism to the other. So in other words, when this equilibrium shifts from RO2 back to R plus O2, and then R undergoes beta scission to give you a smaller an olefin and a smaller radical, either methyl or H ultimately, right? At equilibrium, the addition forward and decomposition reverse reaction rates are equal. So the rate constant for addition times the concentration of R times the concentration of O2 is equal to the rate constant for dissociation times the concentration of RO2. Okay, so if we go ahead and we rearrange that equation, we can write it like this. That's approximately equal to, so if we put in the rate constants then that we have these numbers here. So then we can calculate a pressure at which this they're equal when they're at equilibrium, right? So the pressure at equilibrium is equal to RT all over the fraction of O2 times this number here. And where the pressure is in atmospheres, R is equal to 0.0821. That's the number I was looking for there, okay? Liters per atmospheres per degree Kelvin per mole, okay? And so what happens is, let's just pretend we're at 1,000 Kelvin, for argument's sake, right? So if we're at 1,000 Kelvin and at low pressure, what happens is we're below that equilibrium, and so the equilibrium lies to the left. We have R plus O2 giving us RO2, we have no RO2, we have R plus O2, and alkyl radical is going to undergo beta scission and not add to O2 to give RO2. Okay? If we go higher in temperature, higher in pressure, we'll reach a point where we're at equilibrium. And then if we go higher in pressure, now the equilibrium shifts to the right and we will produce RO2. Okay? It might be better to think. So this ceiling pressure or equilibrium pressure shifts to higher temperature with pressure. Okay? So as you go higher in pressure, the equilibrium shifts to higher temperature.
Is this plot independent of fuel species?
Largely, yes. Yeah. Okay. And I'm just showing it here. Okay. Now, this isn't right, but you can see for similar reasons. Here you have data for N-heptane. The turnover here is at 13 atmospheres. I should be looking out here, actually, at 1250 Kelvin. Okay. Not this one. Okay. I should take out that slide because it's just going to confuse you. Okay, it's really this ceiling temperature out here that's going to shift. All right? Okay, so another thing then, and let me finish, I'll finish soon now when we take a break again. All right, so here's another plot. So this is published, we published this in 2021. Okay, here's 1-pentene, the reactivity. So that's the slowest to ignite, okay, here. Here we have 1-hexene, okay. The model isn't predicting it right, maybe within the error bars. But certainly both the model and the experimental results say that 1-hexene is faster to ignite than 1-heptene. Sorry, 1-pentene. Okay. But if we look at the corresponding alkane, we have 1-hexene here, and we have N-hexane. And N-hexane are these half-filled triangles, and it's way faster than 1-hexene, right? And then we have 1-heptene, which are these diamonds, and then we have that's the model prediction of 1-heptene. And then I don't have the experiment on the data points for the experiment, but we have the model predictions for N-heptane. The model prediction for N-heptane is much faster down here. Now, it actually turns over here, but you can see that N-heptane is predicted to be much faster in the low temperature regime. So why is it that the alkene, so 1-pentene, or we say 1-hexene and N-hexane have different reactivities? And you can see clearly that in this temperature range, 800 to 900 Kelvin, 1-heptene is much slower than N-hexane, its corresponding alkane, right? And the reason is because of this diagram, the R plus O2 giving RO2 equilibrium. Okay, so when R reacts with O2, it falls into this well. So again, this is zero energy barrier. And then Professor Faravelli had shown that this was about 28 kilocalories per mole. It's actually higher. It's about 35 kilocalories per mole, right? So if we look here, sorry. Okay. I'm not going to do it. I think the easiest way to do it for me, if you do the calculation, right? If you consider an alkyl radical, where am I? Yeah. Okay, I'll do it this way. So, okay. Here we have 1, 2, 3, 4, 5 N-pentane, right? The secondary CH bonds have bond strengths of about 96 kilocalories per mole, right? So here, they're both 96. But here in 1, 2, 3, 4, 5, right? This is 1-pentene. This secondary hydrogen atom is 82.5 or 83 kilocalories per mole, right? It's much weaker. It's weaker by 13 kilocalories per mole. Why? Because it's allylic, right? So the hydrogen is bonded to a carbon, which is bonded to a CD, right? Right? So if we abstract this hydrogen atom, we get a radical site here, and now we get electron delocalization, and we have a resonantly stabilized radical, right? Does everybody follow that, right? So, and in olefins, the allylic hydrogen atoms are always the weakest to be abstracted. And when you're at low temperature, because they're the weakest, they're by far the most dominant radical formed, right? Because the Ray constant is going to be very sensitive to the activation energy, and the activation energy for abstraction of a secondary allylic or an allylic hydrogen atom is going to be way lower than that of an alkyl hydrogen, okay? Because the bond strength. Because once you form the radical, it's resonantly stabilized, and hence it weakens that CH bond by 13 kilocalories per mole, right? And so if then we're going to form the alkyl peroxy radical, or the radical, in this case, the alkyl peroxy radical or the allylic peroxy radical, I've actually calculated it here, so I have it right. So if I go back to this, where am I? This well depth, in the case of the alkane, is 36 kilocalories per mole, right? Okay, so for the alkane, the well depth is 36 kilocalories per mole. which makes that very stable. So we get RO2, R plus O2 giving us RO2. So just think of RO2 and then a well depth of 36 calories. It's very deep. You can't get out of it. You're kind of stuck at RO2. Whereas for the olefin, if we abstract the allylic hydrogen atom and we add to O2, the well depth is something between 19.4 and 19.7, 19.55, right? Okay, so 19.5 kilocalories per mole as opposed to 36 kilocalories per mole, right? It's 17 kilocalories per mole shallower, right? So that means that the equilibrium lies much further to the left, to R plus O2, and not to RO2, okay? So in the case of alkanes, it likes to stabilize to RO2. In the case of the olefins, it does not like to form, you won't get as high concentrations of RO2, okay? And therefore, you won't get chain branching because it can't, if you don't get RO2, you can't get QOH, you can't get branching, all right? And hence, the reactivity of the olefins are always slower than that of the alkanes. Okay. And that's probably a good place for me to stop for now.